order for the second part of today's session. In a minute we're going to go over to the rig and we're going to take some open circuit and closed circuit test measurements. So you've got these in the notes on the next 2 pages in the notes. And so take primary power, primary voltage, primary current and secondary voltage when the output is open circuit. Then we're going to short circuit the secondary and take care not to have too much current flowing in the secondary and overload the transformer. We're going to take primary voltage, primary current and power in watts, and then you'll come back over here and carry out the analysis and develop a model of this transformer under load, with a load referred to the primary side. The value of load resistor you're going to use is 546 ohms nominally. Yeah, so eventually the resistor that you're going to analyse connected to the secondary is 546 ohms. So just make a note of that somewhere. We'll pause the video now, go over and get the results, and we'll come back and add them in afterwards. Right, so just for completeness, we'll fill this in. What did we get on open circuit tests for primary power? 2.6 watts. And the voltage we set at 400, didn't we? Primary current in milliamps was 19. And the secondary voltage 251 volts. Okay, so if those of you watching the video now would like to just pause and see if you can do these calculations here to work out the parameters for the open circuit model, like so, and importantly get the value of A that we need for the analysis of the on-load conditions. So let's just check through that and see if we both concur. We've got our measured primary power, 2.6 watts. Calculating the apparent power, 7.6 VA, multiply the current and voltage together, use that value here with the measured power to find Q, 7.14 var. Use the voltage squared and the power to find a value for the parallel resistor that is the core loss. Iron losses in the core, 61.5 kiloohms. To 3 significant figures, it's plenty accurate enough. And then find the value of the magnetising reactance from EP squared over QM. 400 squared over that, 22.4 kiloohms. Just rewrite that. 22.4 kiloohms. Again, to 3 significant figures. And lastly, from the transformer ratio A, which we need for our transfer and impedances stuff, 1.6. The primary voltage over the secondary voltage. Okay, so you all hopefully got those results. So moving on to the short circuit test. What value did we get or what value did we apply on the primary side? 40 volts. So a much lower than nominal voltage. That way keeping the secondary current low. Primary measured current at 40 volts was 246 milliamps, and the power on the measured on the primary side under those conditions was 7 watts. Okay, so now you can use those values to do this analysis here to find values for R primary and X primary that we can use in our final model to analyse the on-load conditions of this transformer. So I'll pause the video here for those watching it, have a go at doing those calculations. Okay, so just checking that we've both got the same results. We found the overall impedance of the connected transformer under these conditions by dividing the second short circuit current by the short circuit voltage by short circuit conditions current. Get 163 ohms. Agree with that? Yeah. RP is then the measured power over the current squared. Get 116 ohms. We then use the total impedance and that resistance in the triangle formula here to calculate a value for XP. I get 115 ohms. Okay, and I can tell you, despite using a slightly different input for the short circuit tests that I used when I gave this a go yesterday, we got within an ohm or two, we got exactly the same results for those two component values. So choosing the choice of that value doesn't make any kind of significant difference. Okay, so what we're going to do now is transfer those values onto the model and go through the same process we did with the example question to find out what's going on with this secondary, what the power input and power output are, see if we can find what the efficiency of this transformer is, and we go and measure those results and see how close we are. Here? Yeah. So if it just depends how you've rounded the other figures. Yeah, it's not going to make a significant difference. Alright? So what we do now is transfer those values onto here. So R was 100 and what? Was it? On the previous page. So 116 then. And X was 114, wasn't it? On mine, I better put what I got on mine. 116 and 115, yeah. Okay. Just make a note here. ZL was 546 ohms. So therefore Z dash is 1.6 squared times 546 equals 11397 ohms. So that's the reflected load that we need in the model to do the analysis. So we transferred those to that model. Now go on to calculate the total predicted primary current, the secondary current under load, the voltage at the secondary terminals under load, and the active power dissipated by the load resistor. So carry out that analysis, and then when all of that is done and we check through it, make sure you and I get the same results, we'll go over there and measure it and see how close we are. And on the very last page I've included a table for us to compare the calculated values with the actual measured values. Okay?